Hey friends, IBM is here with another episode of Learning Physics, and today I would like to conclude with a new particle physics. Do not forget these are solved past paper questions. This is AS level, and this is going to be specifically paper 2. We are starting with the particle physics in these episodes of AS because I believe particle physics is the easiest, and when you master it, there is nothing much to do about it. You just wait for the exam. So do not forget to share these videos with your friends. Do not forget to subscribe. The document for the past paper questions is attached in the video description at the bottom. So do not hesitate to go to the video description, check out the link. Just paste it in your browser, the document automatically opens for download. There's no copyright about with the document. It is just completely free. Just to print and you follow the videos when you have a hard copy of the document. So this is particle physics, and this is actually part 2 of these episodes, and this is going to be the last part in particle physics. I mentioned in part 1 that particle physics must be it could be the last topic in AS, depending on how your teacher wants it. But it doesn't matter how how these videos will be recorded. You may decide to choose which video to start with. So throughout these videos, remember we said we shall see questions relating to Rutherford's alpha scattering experiment, videos relating to the nuclear mode of the atom. We shall talk about isotopes many times. We shall talk about alpha, beta, and gamma radiation as many times as possible. Don't forget we shall be mentioning quarks, that is the quark mode of the atom, and so many more. So do not hesitate to download the document and practice the questions as you prepare for your exams coming this February, March, or May, June next year. So without wasting time, let me take you to the document. And this is the past paper document that I expect that you have already downloaded and maybe printed a copy of yourself. We stopped on page 522 in part 1. So in part 2, we shall start with 523. And this is our first equation. A stationary nucleus of a radioactive isotope X decays by emitting an alpha particle. Remember, an alpha particle is a helium nucleus. An alpha particle is a helium nucleus, which is He42. Or you can write alpha 42, that is fine. You must know how to write an alpha particle, even though you are not a chemistry student. To produce a nucleus of neptunium 237 and 5.5 mega electron volts. Remember, mega is a unit for energy in A level, not in AS, but for now we shall just know. We know that 1 mega electron volts is 1.6 times 10 power negative 13 if you try to change in joules. The decay is represented by X equals to that, plus an alpha particle, which is 42, plus 5.5 mega electron volts. Calculate the number of protons, the number of neutrons in a nucleus of X. So we know X, let this be nucleon number be Z, nucleon number be A, proton number be Z. So when we try to balance to conserve proton number, we have that Z plus, Z on the left hand side should be equal to 93 plus 2, which is giving us 95. So proton number is going to be 95. Proton number is going to be 95. The nucleon number, we have A is going to be equal to, that is A on the left hand side should be equal to the right hand side, which is 237 plus 4. And this is going to be 241. So that is A, but we want the number of neutrons. So number of neutrons is equal to nucleon number minus proton number. So that would be 241 minus 95, which gives us 146. So the neutrons is 146. Now the challenge is people will forget and they will read neutrons as nucleons. That is unfortunate. Explain why the energy transfer to the alpha particle is as kinetic energy is less than 5.5 mega electron volts. If the energy of the reaction or given in the reaction is 5.5 mega electron volts, yet we have products which could also be having kinetic energy, then it means the energy transferred to the alpha particle cannot be 5.5. So the Neptunium could also be having kinetic energy, or there could be a gamma radiations given out during the process. So we can simply say, where was the symbol? Okay, the symbol is this one. We can simply say that NP also has, or NP nucleus has kinetic energy, or we can even add gamma radiation is produced. If gamma radiation is produced, it means some of the energy is given out as gamma radiation. So not all the energy is given out as kinetic energy of the alpha particle, because there could be gamma radiation produced, or other products like NP or Neptunium could be having kinetic energy, which makes the kinetic energy of the alpha to be less than 5.5. A sample of X is used to produce a beam of alpha particles in a vacuum. The number of alpha particles passing a fixed point in the beam in a time of 30 seconds is 6.9 times 10 power 11. Actually, the average current produced by the beam of alpha particles. Average current. By definition, current is the rate of flow of charge carriers. And total charge is actually the number of charge carriers times the charge of one particle divided by T. Since we want the average current, so this is going to be, there are 6.9 times 10 power 11 particles, so that is 6.9 times 10 power 11, but each alpha particle, remember an alpha particle is positive 2e in charge. It is a helium nucleus, He42, the charge is positive 2e. So here we shall set times the charge, which is 2 times 2, it is 2e, and e is 1.6 times 10 power negative 19. This is going to be divided by the time, which time is 30 seconds. So I just take my calculator. And from my calculator, this is 7.4 times 10 power negative 9. Determine the total power in watts that is produced by the decay of 6.9 times 10 power 11 nuclei of X in that time. We want total power. We know that power is equal to energy divided by time. So we need total energy. Remember, the energy of one energy of one reaction is given as 5.5 times, since it was in mega, we change it to joules, so it is times 1.6 times 10 power negative 13 to change it to joules, but that was for a reaction where one alpha particle is emitted. But these are 6.9 times 10 power 11 alpha particles which are being emitted. So I will multiply this by the number. This is the energy when one alpha particle is emitted. And the energy when all of them are emitted is going to be times 6.9 times 10 power 11. And this will be divided by time, which time is 30. So from my calculator, I am getting a 0.020. You can also check with your calculator. I add this 0 here because the answer is not exact. I desist writing any answer which is not exact to less than 2 significant figures. Okay, the results of the alpha particle scattering experiment provide evidence for the structure of the atom. Result number 1, the vast majority of the alpha particles pass straight through the metal foil or are deviated by small angles. Number 2, a very small minority of alpha particles is scattered through angles greater than 90 degrees. Those are the results of the alpha particle scattering experiment. State what may be inferred, that is deduced, from result number 1. Of course, result number 1, if most of the alpha particles pass through, it is only because most of the atom is entirely empty space. Most of the atom is entirely empty space. I'm poor at writing Y and G. Most of the atom is entirely empty space. Number 2, result number 2, a very small minority of alpha particles is scattered through angles greater than 90 degrees. Of course, here we conclude that most of the mass of an atom is concentrated in a small, positively charged nucleus. Most of the mass of an atom is concentrated in a very small, positively charged nucleus. So those are the conclusions from the observations got from the alpha particle scattering experiment. If most of the alpha particles went straight through with little or no deviation, it's because most of the atom is entirely empty space. And if a very small minority of alpha particles is scattered through angles greater than 90 degrees, it is simply because most of the mass of an atom is concentrated in a very small positively charged nucleus. A radioactive decay sequence contains 4 nuclei, P, Q, R, and S, as shown here. So we see that P decays into Q, and we see proton numbers reduced by 2, nucleon numbers reduced by 4, so it has emitted an alpha particle. Then Q decays into R, proton numbers increased by 1, and nucleon numbers not changed, so this must be beta. This must be beta mine. It has emitted beta. I think this is beta plus. No, beta minus. Then R is decaying into S, but they said nucleus S is an isotope of P, meaning S has the same proton number 84. Determine the proton number and the nucleon number of nucleus S. Since it is an isotope, isotopes have the same proton number. So since P has proton number 84, S should also be having proton number 84. And of course, we can predict the nucleon number. We can predict the nucleon number. The only particle this will emit so that the proton number becomes 84 must be beta minus. And therefore, this nucleon number is going to be the same as this one, 214. Therefore, this is going to be 214 because it has emitted another beta minus for the proton number to be 84. It has emitted another beta minus. So the nucleon number is 214, although the proton number is the same as that of P. The quark composition of a nucleon in Q changes as Q decays to form R. The quark composition of Q changes as Q decays to form R. You see that it's decaying by emission of beta minus. Beta minus is emitted when a neutron changes into a proton. While we have gained one more proton, meaning we have lost a neutron. So the quark composition of a nucleon in Q changes as Q decays to form R. Describe the change the quark composition of the nucleon. So since a neutron is changing to a proton, or we are gaining a proton, we are moving from 82 protons to 83, so we are gaining a proton, so a neutron must be lost. A neutron has been changed into a proton, so and the neutron, remember, it has quarks up, down, down. Yet a proton has quarks up, up, down. So they want us to describe the quark composition of the nucleon, the change in the quark composition. So it means up, down, down, changes to up, up, down. Or you can just write up, down, down to up, up, down. Or you can simply say an up quark changes to, a down quark changes to an up quark. Down quark changes to up quark. Okay. A proton in the nucleus decays to form a neutron and a beta positive particle. State the name of another lepton that is produced in the decay. So a proton is decaying into a neutron to give us beta plus. This is a positron. A positron is accompanied by a neutrino or an electron neutrino. So the other particle is going to be an electron neutrino. Or simply a neutrino. I know some of you will say an electron instead of an electron neutrino. Or simply a neutrino. State the name of the interaction that gives rise to this decay. Of course, for these interactions, these are short-range forces required. And because these reside in the nucleus, the interaction is called the weak nuclear interaction or nuclear force. It is the weak nuclear interaction responsible for beta decay. State which of the three particles, proton, neutron, or beta plus, has the largest ratio of charge to mass. We can check. Start with the proton. Proton charge is E. The mass is 1U. That is for proton. A neutron, the charge is 0. The mass is 1U. An electron, a beta particles are fast-moving electrons. The charge is E or negative E. The mass of a beta particle is very small. It is around 1/1840 U. This is a very small value, or it is around 0.0005, I think. You can check 1 divided by 1840. It's around 0.0054. Or you can use 9.11 times 10 power negative 31 in kilograms. This was in U, unified atomic mass units. So you see that this denominator is too small for a beta particle. This was a proton. This is a neutron, and this is the beta particle, the beta positive. So this is of course almost 0 because it has no charge. So the charge to mass ratio is 0. This is approximately E, and this one is the largest, of course. So it is going to be beta plus. Use the Quark model to show that the charge on the proton is positive E where E is the elementary charge. So for a proton, we know that a proton has quarks up, and down. So total charge is going to be an up quark is positive 2 over 3e plus another one which is 2 over 3e plus a down quark is negative 1 over 3e. Of course, LCM is 3, and this is 2e, that is 4e minus 1e, which is 3e, and that gives us positive e as total charge. So you need to know the charges of an up and down quark and a strange quark. The quark composition of the proton is changed during the decay. Describe the change to the quark composition. So they have told us that a proton in the nucleus decays to form a neutron. So it is a proton which is up, down, changing to up, down. So we simply say up, down, changes to up, down. Or you can simply say, you can just write this up, down to up, down, as simple as that. So an up quark in the proton changes to a down quark, so it's no longer a proton, it would rather be a neutron. Okay, one of the results of the alpha particle scattering experiment is that a very small minority of the alpha particles are scattered through angles greater than 90 degrees. State what may be inferred about the structure of the atom. Of course, this one we have already mentioned. This means that most of the mass of an atom is concentrated in a very small positively charged nucleus. That's why when some alpha particles, which are very few, come close to the center of the nucleus, they are deflected through large angles greater than 90 degrees. So we simply say that most of the mass of an atom is concentrated in a small positively let me add emphasis in a very small positively charged nucleus. Okay, that is the conclusion. An alpha particle is made up of other particles. One of these particles is a proton. State and explain why the proton is a fundamental quantity. Of course, we have already seen that a proton has other particles, which is up, down. These are quarks. So we cannot believe that a proton is a fundamental particle, because a fundamental particle cannot be broken down into something simpler. It is the smallest that we have. A fundamental particle is not made up of any other particle. So a proton is not fundamental because it's made up of quarks. So it is made up of quarks. It is made up of quarks, so not what? So not a fundamental particle. It is not even a neutron is also made up of quarks, so it is also not fundamental. So a proton and a neutron are not fundamental particles because they are made up of quarks. A radioactive source produces a beam of alpha particles in a vacuum. The average current produced by the beam is 6.9 times 10 power negative 9 amperes. Calculate the average number of alpha particles passing a fixed point in the beam in a time of 1 minute. So the time is 1 minute. So we know that we want the average number of alpha particles. Remember, an alpha particle is a helium nucleus. It is He42, meaning the charge is positive 2e. The charge is positive 2e. And remember, E is the elementary charge. So we know that charge is equal to current times time. And we see that the current is 6.9 times 10 power negative 9, then times time, which is 1 minute, and 1 minute is 60 seconds. So the total charge is 6.9 times 10 power negative 9 times 60. Remember, one alpha particle has a charge of positive 2e, or positive 2 times 1.6 times 10 power negative 19. So the number of alpha particles is therefore going to be the charge, which is 6.9 times 10 power negative 9 times 60, divided by the charge of each alpha particle, which is twice E, which is 2 times 1.6 times 10 power negative 19. So check on my calculator. So on my calculator, the number of alpha particles is going to be 1.3 times 10 power 12. 1.3 times 10 power 12. The alpha particles in the vacuum in C enter a uniform electric field. Remember, electric fields is now completely A level, not AS. The alpha particles enter the field with their velocity in the same direction as the field. State and explain whether the magnitude of the acceleration of an alpha particle due to the field decreases, increases, or stays constant as the alpha particle moves through the field. Of course, since the field is a uniform field, it means the field strength is constant. And the force in this field depends on this field strength. In fact, it is charge times electric field strength. Remember, force is equal to mass times acceleration, meaning that A is directly proportional to E. So state and explain whether the magnitude of the acceleration of the alpha particle due to the field decreases, increases, or stays constant. Since it is a uniform field, the field strength is constant, the mass of the alpha particle will not suddenly change, so the acceleration is going to be constant. So we can say the magnitude of the electric force is constant. The magnitude of the electric force is constant, so the magnitude of acceleration is constant. So the magnitude of acceleration stays constant. Okay, of course, such a question we expect it mostly in A level now, but for completeness, we shall just answer it. A nucleus X is an isotope of a nucleus Y, so they have the same proton number. The mass of nucleus X is greater than the mass of nucleus Y. Both of the nuclei, so they have different nuclear number, of course. Both of the nuclei are in the same uniform electric field. State and explain whether the magnitude of the electric force acting on nucleus X is greater than, less than, or the same. So, of course, force is charge times electric field strength. It is a uniform field, is the same. The charge of a particle is determined by the proton number. Since they are isotopes, they have the same proton number. So they have the same charge. Even though they have different masses, they have the same charge. State and explain whether the magnitude of the electric force acting on the nucleus X is greater than, less than, or the same. Of course, this is going to be the same. So we say nuclei, because they are isotopes, they have the same charge. They have the same charge since they have the same proton number. The nuclei have the same charge since they have the same proton number, so magnitude of force is the same. Remember, I have derived this from force being equal to charge times E. The electric force is charge times the electric field strength. Okay. Next, state the quark composition of a proton. Of course, this is now easy. A proton has up, up, down. Then a neutron, that is up, down, down. Then an alpha particle, we know that an alpha particle has two protons. This is a helium nucleus, He42. It has two protons and two neutrons. It has two protons and two neutrons. That means this is going to be 2 into up, up, down, plus 2 into up, down, down. Because the neutron has up, down, down, and the proton has up, up, down. So there are two of them. So when you simplify this, you have here in the first bracket you have 4 up and 2 down. In the second bracket you have 2 up and 4 down. Because there are 2 down here times 2, that is 4. There are 2 up here times 2, that is 4. So you combine the up quarks, those are going to be 6 up. Then you combine the down quarks, those are going to be 6 down. So an alpha particle has 6 up and 6 down. So this is the final answer here. In the alpha particle scattering experiment, alpha particles were directed at a thin gold foil. State what may be inferred from the observation that most alpha particles pass through the foil. Most alpha particles pass through the foil simply because most of the atom is empty space. So most of the atom is entirely or mostly empty space. Number 2, state what may be inferred from the observation that some alpha particles are scattered through angles greater than 90 degrees. We have already answered this. Most of the mass is concentrated. Most of the mass is concentrated in a very small positively charged nucleus. Okay, so most of the mass is concentrated in a very small positively charged nucleus. A sample of a radioactive isotope emits a beam of beta minus radiation. State the change, if any, to the number of neutrons in a nucleus of the sample that emits a beta minus particle. State the change, if any, to the number of neutrons. A sample of a radioactive isotope emits a beam of beta minus radiation. State the change, if any, to the number of neutrons in a nucleus of the sample that emits beta minus. You can look at a nucleus X. Let's say X emits, its nucleon number is A, proton number is Z. It emits another nucleus plus beta minus. Beta minus is 0, -1. So you see that A does not change. State the change, if any, to the number of neutrons in a nucleus. proton number Z must be +1 so that it balances. So proton number increases by 1. If proton number increases by 1, remember number of neutrons is equal to number of nucleons minus proton number. So if proton number increases by 1, it means nucleon number reduces by 1. So this one decreases by 1. In other words, when an electron is emitted, it is simply because a neutron has changed into a proton. So decreases by 1. The neutron number decreases by 1. Since the proton number has increased by 1, then the neutron number should decrease by 1. The number of beta minus particles passing a fixed point in the beam in a time of 2 minutes is 9.8 times 10 power 10. Calculate the current. By definition, we know that current is the rate of flow of charge. So charge is going to be the number of particles times the charge of each beta particle, which is going to be n times E over T. The number of beta particles is 9.8 times 10 power 10. Each beta particle has a charge of 1.6 times 10 power negative 19. The time is 2 minutes, which is 2.0 times 60 to change it to seconds. I'll check on my calculator. So from my calculator, this is 1.307 times 10 power negative 10 in amperes. To change it to pico, we divide by 10 power negative 12. So this is 1.307 times 10 power negative 10 divided by 10 power negative 12. To bring a prefix, we divide by its value. To remove a prefix, we multiply by its value. I'm bringing a prefix which is pico, so I divide by the value of pico, which is 1 exponent negative 12. And this is 130.7. So this is 130.7 pico amperes. I will just write 130. Suggest why the beta minus particles are emitted with a range of kinetic energies. Of course, we know that when a proton changes into a neutron, a beta particle is emitted, but these beta particles are accompanied by other particles such as the electron neutrino or the electron antineutrino. The energy with which these beta particles are emitted are going to be shared. To be specific, if a proton changes into a neutron, this is 1, 1, this is 1, 0, this is going to be beta plus 0, 1. Beta plus is accompanied by a neutrino. If a neutron changes into a proton, this is 1, 1, this is 1, 0. This is accompanied by beta minus 0, negative 1. This is a normal electron is accompanied by an antineutrino. So beta minus is accompanied by an antineutrino. So the energy with which they are emitted is going to be shared with other accompanying particles such as the antineutrino. So we can say energy is shared with other accompanying particles. In this case, because it is beta minus, we shall specifically say such as the antineutrino. The names of 4 particles are listed below: alpha, beta plus, neutron, and proton. State the name or names of the particle or particles in the list that are not fundamental. An alpha particle is made up of protons and neutrons. Beta plus is an electron, no further particle. A neutron is made up of up, up, down. A proton is made, up, down, down. A proton is up, up, down. It has quarks. So the only the particles which are not fundamental are alpha, a neutron, and a proton. It is only beta plus which is fundamental. State the names of particles in the list that do not experience an electric force when situated in an electric field. A particle only experiences an electric force when it has a charge. If it doesn't have charge, it does not experience the force. So this particle is going to be the neutron. Has the largest charge, the largest ratio of charge to mass ratio. We have already seen that this is the beta plus. Because we checked the ratio, the mass to charge, the charge to mass ratios, and we saw that because the mass of beta plus is very, very small, then the charge to mass ratio is very high. A hadron has a charge of positive E, where E is the elementary charge. The hadron is composed of only 2 quarks. Only 2 quarks. That is most likely going to be a meson. One of these quarks is anti-down. By considering charge, state and explain the name, flavor of the other quark. So the total charge is Q. So we know that a anti-down quark has charge because down is negative 1 over 3e, then anti-down is going to be positive 1 over 3e. Then we can find the other quark by finding its charge first. So we have that total charge is E, total charge equals to E, positive. And this is going to be for anti-down, which is positive 1 over 3e plus the charge of the other quark. So we notice that Q is going to be equal to E minus 1 over 3e. I've made Q the subject, and this is giving me an E minus 1 over 3e, I think, is positive 2 over 3e. So the charge of the other quark is positive 2 over 3e, and this is most likely going to be an up quark. It can be a charm quark or top quark. So we can simply just conclude that. So we can say charge of the other quark is positive 2 over 3e. So it is an up. It is an up quark, or it can be charm, or it can be top. Any of those. Of course, the most common one is up. We know up, down, and strange mostly. But there's also charm and top. State and explain whether a neutron is a fundamental particle. Of course, a neutron has up, down, down, so it is not fundamental. So not fundamental. Not a fundamental since it is made of quarks. It's not fundamental since it is made up of quarks. A proton is a stationary nucleus. In a stationary nucleus, decays. State the 2 leptons that are produced by the decay. So when a proton decays, it is going to give us a neutron. So a proton is 1, 1, a neutron is 1, 0, plus we balance the equation. This will be beta 0, so beta plus, I think, 0, positive 1. So it is going to give us a positron or beta plus, and beta plus is accompanied by an electron neutrino. Of course, this has no mass, it has no charge. So this is giving us beta plus, or you can write beta plus or positron. That's 1. Then 2, it is giving us an electron neutrino. An electron neutrino is represented by that. When you put an E there, it is fine, or you may not put the E here, but that is an electron neutrino. It's like a V which is slightly twisted. Part of the energy released by the decay is given to the 2 leptons. State 2 possible forms of the remainder of the released energy. In which form does the remaining energy take? Because part of the energy is released by the decay. Part of the energy released by the decay is given to the 2 leptons. So the leptons will have kinetic energy. So we can say kinetic energy of the nucleus. It can also take form of gamma radiation. Energy mostly takes form of kinetic energy of the products or the recoil of the parent nucleus or gamma radiation. Okay. Use the Quark model to show that the charge on a proton is positive E. Use the Quark model to show that the charge of a proton is positive E. A proton has up, up, down, so charge is going to be equal to an up quark has positive 2 over 3e plus another up 2 over 3e plus a down quark which is negative 1 over 3e. And this is going to be positive 3e over 3e, which is actually positive e. As simple as that. Then the neutron, a neutron has up, down, down. The charge is going to be positive 2 over 3e plus negative 1 over 3e plus negative 1 over 3e, which is going to give us 0 over 3, which is equal to 0. So the charge here of a neutron is 0. A nucleus of SR decays by the emission of beta minus particle. A nucleus of Cu decays by emission of beta positive particle. In the figure, state the nucleon number and proton number for the nucleus produced in each of these decay processes. Beta minus. So SR, it is 90, 38. It is decaying by giving us beta minus, which is 0, negative 1, plus a new nucleus, Y. State the nucleon number and proton number for the nucleus produced. So Y, nucleon number will not change. So for the first part, when beta minus is emitted, nucleon number remains 90, but the proton number will now be 38 plus 1, which is 39, in order to balance on the left-hand side. So this will be 38 plus 1, which is 39. Then the other side, we have beta plus. So we have that Cu 6429 is giving us beta plus. Beta plus is 0, 1, plus a new nucleus Y. Nucleon number remains 64. Proton, so this is 64 to balance. This one, because on the left it is 29, on the right should also be 29, so this will be 28. So the answer here is going to be 28. State the name of the force responsible for beta decay, that is the weak nuclear interaction. State the names of the leptons produced in each of the decay processes. Beta minus decay. Remember, beta minus decay, we know that a proton, not a proton, yeah, a proton. No, beta minus is not a proton, it is a neutron. So beta minus, we have that a neutron changes to a proton. So this is 1, 0, 1, 1. So when we add, this will be beta minus 0, negative 1. And this is accompanied by an antineutrino. So beta minus, this is a normal electron. So this is electron and antineutrino. So that is an electron and antineutrino, because an electron is a lepton and antineutrino is a lepton. Then a beta plus decay, that is a proton, changes into a neutron. So 1, 1, 1, 0, giving us beta plus 0, positive 1. This is accompanied by a neutrino. So this is a positron. Positron is the antiparticle of the electron, and the positron is accompanied by an electron neutrino, or simply a neutrino. It is accompanied by an electron neutrino, or simply a neutrino. There is an I there. Next, describe two differences between the decay of a nucleus that emits a beta minus particle and the decay of the nucleus that emits a beta positive particle. We want differences. This is a similar question to the one we have just seen above. Let's start with the beta minus emission. For beta minus emission, we know that a neutron changes to a proton. A neutron changes to a proton. We have seen it here. Beta minus, a neutron changes to a proton, and we have seen that an antineutrino is accompanied. And for beta positive, we are still on the same difference. For beta positive emission, a proton changes to a neutron. So that's one difference. Difference number 2. For beta minus, we have seen it is accompanied by an antineutrino. For beta plus, it is accompanied by a neutrino. So we shall say again, beta minus emission, electron antineutrino is also emitted. And then for beta plus emission, the electron neutrino is also emitted. So those are the two differences. I don't think there is any other common one. In a simple quark model, there are 3 types of quarks. State the composition of the proton and of the neutron in terms of these 3 quarks. Of course, we now know for proton, that is up, up, down, and of course there is zero strange. And we have for neutron up, down, down, there's also zero strange. The following particles are used to describe the structure of an atom: electron, neutron, proton, quark. Underline the fundamental particles in the above list. We start with an electron. An electron is not broken down into anything simpler. A neutron has up, down, down quarks. A proton has up, up, down. A quark is a smaller particle, so we have a quark and the electron. Those are the fundamental particles. These ones are not broken down any further. That's why we are calling them fundamental particles. The following equation represents the decay of a nucleus of CO to form a nucleus Q by beta minus emission. Complete the figure. Complete the figure. So A, we are looking at we are just trying to balance. Beta is 0, -1. So A plus 0 is equal to the other side. So A is going to be 60. And B minus 1 should be equal to 27. B minus 1 should be 27. So B is going to be 28. State the name of particle X. Note that this is an electron. An electron is accompanied by an antineutrino. So this is electron antineutrino, or simply antineutrino. A beta minus particle from a radioactive source is traveling in a vacuum with kinetic energy 460 electron volts. Remember, 1 electron volt is the same as 1.6 times 10 power negative 19 in joules. The particle enters a uniform electric field at a right angle and follows the path shown there. The direction of the electric field is in the plane of the paper. Note that the particle is negative and the path is upwards. So most likely this is positive, the bottom is going to be negative, or lower potential. On the figure, draw an arrow to show the direction of the electric field. Of course, a negatively charged particle moves in the opposite direction to the electric field. So since it is moving upwards, then the electric field is going to be downwards. So the direction of the electric field is downwards. Calculate the speed of beta minus particle before it enters the electric field. So before it enters the electric field, it has kinetic energy, which is given by the accelerating PD. And the kinetic energy is given as 460 electron volts. We know that kinetic energy is going to be a half mv squared, which means that V is going to be twice the kinetic energy divided by m under the square root. So I just substitute square root of 2 times the kinetic energy is 460. I change it to joules, that is times 1.6 times 10 power negative 19 divided by the mass. Beta minus, that is an electron, whose mass is the mass of the electron, which is 9.11 times 10 power negative 31. So I press the calculator. So from my calculator, I get the speed as 1.3 times 10 power 7. Other beta minus particles from the same radioactive source travel outside the electric field along the same incident path as that shown in the figure above. So there are beta particles are moving along the same path. But note that we know that beta particles are emitted with other accompanying particles, so they have a range of energy. So we expect them to take different paths. State and briefly explain whether these beta minus particles will all follow the same path inside the electric field. Because they have a range of energies, when they enter the electric field, they're going to have different, actually they're going to have to undergo different, let me say, they will have actually different speeds, different energies. So when they enter the electric field, they will not follow exactly the same paths. So we shall simply say that beta minus particles, just like beta plus particles, beta minus particles have a range, of energies. Have a range of energies or speeds. Of course, since speed is momentum is mass times velocity, so when I say range of energies, that implies speeds, that implies momenta. So beta minus particles have a range of energies, they have a range of speeds, or they have a range of momenta. So they may follow different paths. So they may follow different paths because they have a range of energies. Okay. A stationary nucleus X decays to form nucleus Y, as shown by that equation. In the above equation, draw a circle around all symbols that represent a lepton. Of course, leptons, those are fundamental particles which are not broken down any further. So this is beta minus. Beta minus is an electron. An electron is a fundamental particle. It is a lepton. And this is the antineutrino. An antineutrino is also a lepton, so we circle those two. State the name of the particles represented by the symbol. The symbol are that is an electron antineutrino, or simply antineutrino. It's an antineutrino. Energy is released during the decay process. State the form of energy that is gained by nucleus Y. Of course, we said energy takes on basically two forms, but now nucleus Y must automatically gain kinetic energy. It can't gain energy in form of gamma ray photons. So the nuclei are emitted with kinetic energy. If there is a balance, then it is emitted as gamma radiation. So Y takes on kinetic, or has kinetic energy. By comparing the compositions of X and Y, state and explain whether they are isotopes. Let's check. X is decaying into Y. X nuclear number is A, Z number is Z, or proton number is Z. It is giving us beta minus, which is 0, -1. So nuclear number is the same. Proton number, this is Z plus 1. So Y has one more proton than X. So proton number is not the same, so they can't be isotopes. So we can say Y has one more proton. One more proton. Y has one more proton. And of course, if it has one more proton, it has one less neutron than X. And one less neutron than X. So they are not isotopes. Remember, isotopes must have the same proton number but different nucleon number or different neutron number. Although they have different, they don't have the same proton number, so they cannot be isotopes. The quark composition of one nucleon in X is changed during the emission of beta minus. Emitting beta minus, a neutron is changing into a proton. Neutron changing into a proton. This is 1011 plus beta minus. This is beta minus. So a proton, a neutron changes into a proton. Describe this change to the quark composition. So since a neutron is changing into a proton, so we just change from up, down, down to up, up, down. In other words, a down quark changes. A down quark changes to an up quark. Okay. A graph of nucleon number A against proton number Z is shown in the figure here. The graph shows a cross labeled P that represents a nucleus P. Let's first see P here. So this is a proton number and this is nucleon number. So P proton number is 84, nucleon number is 214. Okay. Nucleus P decays by emitting an alpha particle. Remember, an alpha particle is He42 to form nucleus Q. So P is giving us an alpha particle. So P gives us Q plus an alpha particle, which is He42. So proton number must reduce to 82. Nucleon number must reduce to 210. Nucleus Q then decays by emitting beta minus. Beta minus is 0, 1, negative 1 I mean. So Q, which is, we have found that Q is 210, 82. It is giving us another nucleus, which is nucleus R by a beta minus. So beta minus is 0, negative 1. Nucleon number does not change. Proton number is going to be 83 because of this negative 1. So the proton number must always be conserved. Okay. On the figure, use a cross to represent nucleus Q and nucleus R. So that is now very easy since we have already calculated this. Q should be proton number 82 and nucleon number should be 210. So Q should be, I think, here. So that is Q. Then R is nucleon number 210 and proton number 83. So R should be here. So that is R. State the name of the class, in bracket group of particles, that includes beta minus. Of course, beta minus is a lepton, so these are leptons. Particles which are not affected by the strong nuclear reaction, they just interact via the weak nuclear interaction. The quark composition of one nucleon in Q is changed during the emission of beta minus particle. Describe the change to the quark composition. So we are moving from beta, we are emitting beta minus. So that is a neutron changing into a proton. You can always check to see that there is balance, because beta minus on the left will make this one to go back to 0 on the right. I mean, beta minus on the right will make the total proton number to be 0, just like it is on the left. So it is a neutron changing into a proton. So what is happening to the quark composition when a neutron changes into a proton? So we move from up, down, down. That is a neutron changes. It changes to up, up, down. Or I just write up, up, down. I mean up, down, down to up, up, down. Or a down quark changes to an up quark. One of the results of the alpha particle scattering experiment is that a very small minority of the alpha particles are scattered through angles greater than 90 degrees. State what may be inferred about the structure of the atom. Of course, If just a very small minority is scattered through angles greater than 90 degrees, it is simply because most of the mass is concentrated in a very small positively charged nucleus. So we say most of the mass of an atom is concentrated in a very small positively charged nucleus. By the way, the nucleus must be charged. The nucleus is charged. So most of the mass of an atom is concentrated in a very small positively charged nucleus. That's why a small percentage are deflected or scattered through large angles. But otherwise, most of the alpha particles went straight through, simply because most of the mass is entirely empty space. A hadron has an overall charge of positive E. A hadron is basically made of quarks, where E is the elementary charge. The hadron contains the three quarks, that is normally a baryon. One of the quarks is a strange. Set the charge in terms of E of the strange quark. Of course, a strange quark has charge -1/3e. I showed you how we know these charges. The word strange, something strange may not easily be pleasant. The opposite of strange is charm, and charm has +2/3e. The other two quarks in the hadron have the same charge. So I'll call their total charge twice q. By considering charge, determine a possible type of the other two quarks. So since the other two quarks are of the same charge, so their charge is going to be twice q plus the charge of a strange, which is -1/3e. This should give us positive e. So using charge, so you notice that q is going to be equal to, when I collect like terms, q is going to be equal to, this will be e plus e plus 1/3e, which is going to be plus twice this is 2q is equal to e plus 1/3e, which is going to be 4e/3. So we have that twice q is equal to 4e/3. So q is going to be 2. So the charge is q is plus 2/3e. So this is basically an up quark or a charm or top. So determine the possible type of the other two quarks. So that is, those are going to be up quarks, because it is up quarks with this charge, or it can be charm, or it can be top, but these are not commonly used. So because of the charge, that is an up quarks. A sample of radioactive substance may decay by the emission of either alpha, beta, or gamma radiation. State the type of radiation, one in each case that consists of leptons. Alpha has protons. Beta radiation, those are actually leptons. Gamma radiation, those are electromagnetic radiations. Beta is electron, so that is a lepton, so this is beta. Contains quarks. Of course, alpha has quarks because it's made of protons and neutrons, so that is alpha. Then cannot be deflected by an electric field. It should not be having charge, so that is going to be gamma. Has a continuous range of energies. It is the beta particles with the ranges of energies because they have different speeds, since accompanying particles are also produced, such as the positrons, the neutrino and the antineutrino. So this is going to be beta. A nucleus of an element X decays by emitting beta plus to produce a nucleus of potassium and a neutrino. The decay is represented by that equation. State the number represented by each of the following letters. P. So this is beta plus, that is 0, 1. So P must be 0. And R must be 1. Then, so we have finished that. Now we balance on the left. On the left we have Q. Q should be equal to 39 plus P, which is 0, plus 0. So Q is going to be 39. Then we have S. S is equal to 19 plus R, which is 1, plus 0. S is going to be 20. So that is as simple as that. Say the name of the interaction that gives rise to beta positive. For beta decay, that is the weak nuclear interaction. Weak nuclear interaction. A hadron is composed of 3 identical quarks. That means they have the same charge. Let's say each quark has charge Q. And it has a charge of positive 2e, so that is the total charge. Determine a possible type of flavor of the quarks. Since they are identical, their charge is going to be 3q. So total charge is 3q, which is going to be positive 2e, which means that q is equal to positive 2 over 3e. And the quarks with this charge are up, charm, or top. So these are going to be up quarks. They are up quarks or charm or top. Although I say this is not common, but they are up quarks because this is a charge for up quarks. The beta minus particle is produced by the decay of a neutron. Complete the equation below to represent the decay of the neutron. Of course, this is -1. This should be a proton, P11, so that the proton number is 0 on both sides. Nucleon number is 1. Then this is a proton, which is this is an electron, which is a normal electron is accompanied by an antineutrino. So this is going to be 0, 0, and this is going to be an electron antineutrino. Because it's an antineutrino, I'll put a bar on top. State the name of the group or class of particles that include neutrons. These are hadrons or baryons. So these are hadrons or baryons. They are hadrons because they are made up of quarks. And they are baryons because they are made up of 3 quarks specifically. So they are hadrons or baryons. Beta minus, these are automatically leptons. They have no quarks. They are fundamental particles. A neutron with a nucleus decays to produce a proton, a beta minus particle, and an electron, antineutrino. So they have showed us here. Use the quark composition of the neutron to show that the neutron has no charge. So quark structure. The quark structure is up, down, down for a neutron. Up, down, down. That is the quark structure. Or just write UDD. And total charge. We know that charge of up quark is positive 2 over 3e. And charge of down is negative 1 over 3e. So total charge is going to be equal to positive 2 over 3e plus positive 2 over 3e plus negative 1 over 3e, which is going to be 0 over 3, which is equal to 0. So neutron has no charge. So the examiner will be able to know that the quark composition, the charge of each of these up and down, and then you sum up to get 0. That's what will give you the 3 marks. Complete the figure by giving appropriate values of the charge and the mass of the proton, the beta minus particle, and the electron antineutrino. Starting with the electron antineutrino, we know that this one has no charge, it has no mass. A beta minus is an electron whose charge is negative E, or negative 1.6 times 10 power negative 19. So this is negative E, or negative 1.6 times 10 power negative 19 coulombs. Then the mass, this is an electron, so it is 9.11 times 10 power negative 31 in kilograms. Or this can be 0.0005 in unified atomic mass units, U, in U. The charge of a proton, the charge is positive E, or 1.6 times 10 power negative 19, and this is positive. And the mass of a proton, of course, the mass is 1.67 times 10 power negative 27 in kilograms. Those are basic facts that you must be knowing by now. A stationary nucleus X decays by emitting a beta plus particle to form a nucleus of carbon. An incomplete equation to represent this decay is X equals to that. This is 0, 1. State the name of the class of particles that includes beta plus. Of course, beta plus, that is lepton, or those are leptons. For nucleus X, state the number of protons. We balance this equation. On the right, proton number is 13. This should also be 13. That is nucleon number. On the right, proton number is 7. This should also be 7. So we want number of protons, that is 7. Number of neutrons, not nucleons, that would be 13 minus 7, which is 6. Do not be confused here, and you write nucleons instead of neutrons. The carbon-13 nucleus has a mass of 2.2 times 10 power negative 6 kilograms. Its kinetic energy as a result of the decay process is 0.8 mega electron volts. Calculate the speed of this nucleus. So they have given us energy. From energy, we can find the speed. Although mega electron volts is a unit for A level, not AS, we shall still use it here. So energy is equal to a half mv squared. We want V. V is going to be 2 times the energy divided by the mass under the square root. So this will be the square root of 2 times the energy, which is 0.80. I'm going to change the energy from mega electron volts to electron volts. 0.80 times, I'll multiply this by 1.6 times 10 power negative 13 to change it from mega electron volts just to joules, divide by the mass. The mass has been given as 2.2 times 10 power negative 26 kilograms. So I press my calculator. So from my calculator, this is 3.4 times 10 power 6. Explain why the sum of the kinetic energies of the carbon-13 nucleus and the positive beta plus particle cannot be equal to the total energy released by the decay process. The sum of kinetic energy of carbon-13 and the beta may not be equal, so maybe gamma radiation is emitted. So also the nucleus may have energy, so it may repair with some energy. Or even there are other accompanying particles such as the electron neutrino. So the most important one is the electron neutrino, which accompanies the beta plus. It also has some energy. So we can say an electron neutrino is also produced and it also has energy. So because the beta plus is accompanied by a neutrino, the neutrino will also have energy or kinetic energy. So this is going to make the sum of kinetic energies of carbon and beta plus not equal to what is released in the decay process, because even the neutrino will have kinetic energy. Okay, remember if it is a beta minus, it will be the antineutrino accompanying it. It will also have energy. A nucleus X decays by emitting a beta plus particle to form a new nucleus, that is sodium 2,3,11. State the number of nucleons and number of neutrons in X. So X is the one decaying by emitting a beta plus. Remember this is 0, 1 plus sodium Na 2311. So we try to balance. Nuclear number here is 23. So nuclear number of X is going to be 23. This is number of neutrons, not protons. Balancing the proton number is going to be 12. So number of neutrons N is going to be 23 minus 12, which gives us 11. So number of neutrons is 11. It is not number of protons. State one similarity and one difference between beta plus and beta minus. Of course, both of these are fundamental particles. They have the same rest mass. They have equal magnitude of charge, 1.6 times 10 power negative 19 coulombs, magnitude. But of course, the charges have opposite signs. We know that beta plus is an antiparticle of beta minus or antimatter of beta minus. Okay, so similarities, they have the same rest mass. Same rest mass, that is the mass of the electron. They have equal magnitude of charge. Magnitude is very important. Equal magnitude of charge. They have equal magnitude of charge. That is, their charge is 1.6 times 10 power negative 19 coulombs in magnitude. However, for differences, they have opposite sign of charge. Beta plus is positively charged, beta minus is negatively charged. That's the one difference. Number two, we know that beta minus is matter and beta plus is antimatter. Or you could say beta minus is an electron and beta plus is an anti-electron. So beta plus is an anti-electron, beta minus is electron. By the one other similarity, you could say both are fundamental particles. Both are fundamental particles. Okay, those are some of the similarities and differences. When you say charge, it should be as a similarity, should be magnitude. But as a difference, charge, they have opposite signs of charge, even though the magnitude is the same. A stationary nucleus X decays by emitting an alpha particle to form a nucleus plutonium. So X is decaying by emitting an alpha particle. Remember, alpha is 42 to form plutonium. Determine the number of protons and number of neutrons in nucleus X. So proton number, this should be 94 plus 2, which is actually 96. So proton number is 96. Nucleon number will be 240 plus 4, which is 244, but the question wants neutron number. So we shall get 244 minus 96, which is 148. The total mass of plutonium nucleus and the alpha particle is less than that of the nucleus X. Explain this difference in mass. What does the difference in mass imply? Of course, the difference in mass implies that mass energy is going to be conserved, because the difference in mass is going to be seen as the energy released in form of gamma radiations or kinetic energy, so that mass energy is always conserved. So the question wants us to explain this difference in mass. Explain this in nuclear physics, we shall see explain it here. So there is a difference in mass because mass energy is always conserved. Mass energy is conserved. Mass energy is conserved. Sorry. Mass energy is conserved. So we are saying that the difference in mass is seen as energy released. Is seen as energy released as gamma radiation or the kinetic energy of alpha. Do we have alpha? Yes, of alpha, or kinetic energy of the plutonium. Or the kinetic energy of plutonium. So energy is seen as, that difference in mass is converted into energy, which is seen as gamma radiation or kinetic energy of the alpha, or kinetic energy of the plutonium. The plutonium nucleus and the alpha particle are both accelerated by the same uniform electric field. So E is the same. This could be a question in electric fields, which is now in A level, but we shall still answer it here for completeness. Use expressions in B to determine. Use the expression in B to determine the ratio acceleration of the alpha particle over acceleration of the plutonium nucleus. So expression in B, I think I removed it because it was more of it was more of electric fields, but of course we can still answer this. So we know that force is mass times acceleration, and the force due to the electric field is Q times E. So it means the acceleration is going to be Q E over the mass. So let's try to find the ratio here. Remember, E is the same because they are entering the same uniform field, so E is the same. So the ratio, we want the ratio of acceleration of the alpha particle, which will be the charge of the alpha particle, which is twice E. Electric field is E over the mass of an alpha particle is 4U. Divide by acceleration of plutonium. The charge of plutonium is going to be plutonium, I think is 90. Plutonium is 94. So charge is going to be 94E. Electric field strength is E over the mass. Nucleon number is 240. So the mass is going to be 240U. 240 times U. So this is going to be E has cancelled, U has cancelled, so we remain with the 2 over 9, 2 over 4 times, we get the reciprocal, which is 240 over 94. And I check my calculator to find this ratio. Note that I have cancelled E when I divide, I have cancelled U, I have cancelled small e, then I remained with that one in the numerator divided by the one at the bottom, so that I get that ratio. When I press my calculator, this is giving me 1.3 as the ratio. In the following list, underline all particles that are leptons. Of course, leptons are fundamental particles. They're not made up of anything simpler. We have antineutrino. It is not made up of anything simpler. It is the simplest. The positron is a beta minus, a beta plus particle. The proton has quarks, so it is not a lepton. And the quark is also not a lepton. So we have antineutron, antineutrino, and the positron. Those are leptons. So the quark together with the leptons form what we call fundamental particles. A stationary nucleus of magnesium-27 decays by emitting beta minus particle and gamma radiation. An incomplete equation to represent this decay is shown here. Magnesium X beta minus is 0, -1, and the gamma radiation. So X is going to be automatically 27. When we try to balance nucleon number, X is going to be 27. Proton number will be 12 plus 1, so that it remains 12. So that is going to be 13. Because 13 minus 1 on the right gives us what is on the left. So proton number is 13. Okay. State the name of the interaction that gives rise to this decay. Of course, this is a beta decay, that is weak nuclear interaction. That is the weak nuclear interaction. State two possible reasons why the sum of kinetic energy of beta minus and energy of the gamma radiation is less than the total energy released during the decay of the magnesium nucleus. We know that beta minus is going to be accompanied by an antineutrino, which will also have energy. That's number one. Number two, the magnesium nucleus may recoil during the production of those particles. So it may also have kinetic energy, or even X could also be having kinetic energy. Therefore, the sum of the kinetic energy of beta minus and gamma radiation is going to be less than the total energy during the decay. So number one, X also has kinetic energy. X also has kinetic energy. That's number one. Number two, we know that an electron antineutrino is also produced and it has energy. So an electron neutrino is produced. An electron neutrino is produced and an electron antineutrino, not neutrino. An electron antineutrino is also produced and it has energy. So the energy is shared with the accompanying particle. State a similarity and a difference between a down quark and an antiquark. A down antiquark. Of course, a quark is a particle and antiquark is an antiparticle. Or quark is matter and antiquark is antimatter. That is the difference. But they have the same mass, they have the same magnitude of charge, and they are both fundamental particles. So we can say similarity, they have the same mass or same rest mass. That's one. Two, they have same magnitude of charge. Same magnitude of charge. The charge of a down quark is -1/3e, and the charge of an anti-down is +1/3e. So the magnitude is the same magnitude of charge. Number three, they are both fundamental particles. They are both fundamental particles. Then difference. Difference, of course, one is positive, negative, +1/3e, that is the anti-up, and the down quark is -1/3e. So we can say they have opposite sign of charge. Opposite sign. The word opposite cannot be replaced by different. Opposite sign of charge. That's one. Number two, down is matter. Down quark is matter. Anti-down is anti-down is antimatter. So those are the differences, n of those two. For a nucleus of aluminium, 25, state the number of protons and number of neutrons. Protons, I think this is a proton number, that is 13. Neutron number, you get 25 minus 13, which is 12. Show that the charge is 2.1 times 10 power negative 18 coulombs. So let's find the charge. The charge is going to be proton number, which is 13 times E, which is going to be 13 times 1.6 times 10 power negative 19. Of course, this is going to give us, let me check for my calculator. Because there are 13 protons, each proton has charge E. So just say 13 times 1.6 times 10 power negative 19. So this is 2.1 times 10 power negative 18 coulombs. State a similarity and a difference between a quark and an antiquark. It is almost the same question as the one we have just seen above. So similarity, they have same rest mass, That's 1, 2. They have the same magnitude of charge. Then 3, they are both fundamental particles. You can't fail to state one of those. Then differences, although they have the same magnitude of charge, they have opposite sign of charge. I said the word opposite cannot be replaced with a different. So opposite sign of charge. Remember, an up quark has a charge of positive 2 over 3e. An anti-up has a charge of negative 2 over 3e. So they have opposite sign of charge. Then number 2, up is matter. An up quark is matter and anti-up is antimatter. So that is a difference. The nucleus of carbon is the nucleus is carbon 14. This nucleus decays to form a new nucleus by releasing a beta minus particle and only one other particle of negligible mass. Calculate the nucleon number and proton number of the new nucleus. So the nucleus is carbon 14. It is giving us another nucleus, I will call it X, plus beta minus, which is 0, negative 1. So nucleon number does not change, it remains 14. Proton number increases by 1, so this would be 7. So that on the left, proton number is 6, and on the right, total proton number is also 6. So the name of the particle of negligible mass. Since it is a beta minus particle is accompanied by an anti-neutrino, because beta minus is an electron. It is accompanied by an electron anti-neutrino. So the other particle is anti-neutrino or electron anti-neutrino. Okay, number next. Complete the table to show the masses in terms of the unified atomic mass unit, that is U, and the charges in terms of the elementary charge E of alpha, beta plus, beta minus particles. Okay, so let's begin with the charges. An alpha particle is a helium nucleus, that is He42. So the charge of an alpha particle is positive 2e. That is positive 2e because there is an e there. Then beta plus, that is positive e. So that is positive 1e. Beta minus is negative 1e. E is already given there. I don't need to write it again. Then a mass. An alpha particle is a helium nucleus, so this is 4u. Beta particles are fast-moving electrons. Their mass is 9.11 times 10 power negative 31. In terms of U, we divide this, this is in kilograms. In terms of U, this is going to be 9.11 times 10 power negative 31 divided by 1.66 times 10 power negative 27. So 9.11 exponent negative 31 divided by 1.66 exponent negative 27. So this is 5.5 times 10 power negative 4, or we can write 0.00055 U, or 0.005. There's no problem with that. 0.00055 U. So that is the mass. Alternatively, I could write this as 1 over 1840. 1 over 1840 U. That is also the mass of these particles. They have the same rest mass. Carbon-14 is radioactive and decays by emission of beta minus. Nuclei do not contain beta minus. Explain the origin of beta minus particle that is emitted from the nucleus during beta minus decay. We know that the nuclei do not have beta minus, but where does the beta minus come from? Remember, a neutron changes into a proton. A neutron is 1, 0, proton is 1, 1, plus beta 0, 0, negative 1. So a neutron decays into a proton and an electron. So a neutron decays into a proton and an electron. That is how we have beta minus. And an electron, thus beta minus particle emitted. So when a neutron turns into a proton, an electron is emitted, which is a beta minus particle. That is the origin of beta minus. State the change in the quark composition of a carbon-14 nucleus when it emits a beta minus. So a neutron has changed into a proton, up, down, down, changes to up, down. So one down quark changes to up quark. Or so just say let me say down quark. A down quark changes to an up quark. Suggest why the beta minus particles are emitted with a range of different energies. We have already seen this. When beta minus is emitted, it is accompanied by, this is an electron, it is accompanied by an antineutrino. So electron antineutrino are also emitted. So the electron antineutrinos are also emitted. So the energy released in the decay is going to be shared between the beta minus particle and the antineutrino. Energy released in the decay is shared between the beta minus particle and the antineutrino. So the energy released in the decay process is going to be shared between the beta minus particle and antineutrino, which means the beta minus particles will have a range of energies. Okay. A stationary nucleus P of mass 243U decays by emitting an alpha particle of mass 4U to form a different nucleus Q as illustrated here. So before decaying and after decaying. The initial speed of the alpha particle is 1.6 times 10 power 7 meters per second. Use the principle of conservation of momentum to explain why the initial velocities of nucleus Q and the alpha particle must be in opposite directions. Note that P was initially stationary, its momentum was initially zero. So the total momentum of nucleus Q and P should be equal but opposite, so that total momentum is conserved and it is always zero. So that's number one. So we simply say that total momentum before decay is zero. Total momentum before decay is zero. So total momentum after decay must be zero. Total momentum after decay must also be zero. Total momentum after decay must also be zero. So the alpha particle and Q have momenta. Momenta is plural in opposite directions. And therefore velocities are in opposite directions. We cannot look at the mass to be the ones dictating the direction of momenta. It is the velocities. And therefore velocities are in opposite directions. So this is just conservation of momentum. If before the decay the total momentum is zero because the nucleus P was at rest, then after decay the total momentum should also be zero by conservation of momentum. Therefore, the alpha particle and nucleus Q should be moving in opposite directions. Therefore, their velocities should be in opposite directions so that total momentum can still be conserved. Determine the initial speed Q. The initial speed V of nucleus Q. So we know that momentum is mass times velocity, and we have that the mass of P was 243 U, and after collision the mass of Q is not known. The mass of Q is what is the mass of Q anyway? Okay, we don't know the mass of Q, but we have the speed of the alpha particle. So since the total momentum of Q should be the same as the total momentum of the total momentum of Q and alpha should be the same as total momentum before the decay, then if this is 243, then we can first write an equation here. 243, nuclear mass of this is 4U, so this is going to be 243 minus 4, which is I think 239U. The mass of Q is 239U, so let me use conservation of momentum. So total momentum was 0. 0 is going to be after. For Q, the mass is 239U times its speed, which we don't know. The other one is in the opposite direction, so I'll put a negative. and the other one is 4u times its speed, which is 1.6 times 10 power 7. So this is minus 4u times 1.6 times 10 power 7. So in other words, we have that 239u times v is going to be equal to 4u times 1.6 times 10 power 7. So you see that u has cancelled out, so we remain with the v. We can find now v by dividing. So from my calculator, this is to two significant figures, 2.7 times 10 power 5 meters per second as v. 2.7 times 10 power 5. Calculate the initial kinetic energy in mega electron volts of the alpha particle. So we now have its speed, of course. Kinetic energy is going to be a half m v squared. This is going to be a half. The mass of an alpha particle is 4u. We want the answer in mega electron volts. We have to change the mass in kilograms. So it will be 4 times 1u is 1.66 times 10 power negative 27. That is the mass. This is mass in kilograms. Then times the speed is 1.6 times 10 power 7, and this should be squared. So answer so this is 8.5 times 10 power negative 13 in joules. Then we have to change this in mega electron volts. So this will be 8.5 times 10 power negative 13 divided by 1.6 times 10 power negative 13 to change it to mega electron volts. So 8.5 divided by 1.6. So the kinetic energy in mega electron volts is going to be 5.3 approximately. A graph of number of neutrons n against proton number z is shown in the figure here. So they have given us P. Let's find P. P has proton number. Our proton number is 95. Neutron number capital N is 148. That means number of nucleons. By the proton number is Z, I will write Z. Number of nucleons, you just add 95 plus 148. So this is 243. That is P. The graph shows a cross that represents nucleus P. A nucleus R has a nucleon number of 242 and is an isotope of P. R, so this is P has 243, 95. A nucleus R is an isotope of P. They have the same proton number, that is 95. But it has nucleon number 242. So we just look for it. So that means its proton number, neutron number N is 242 minus 95. 242 minus 95. 242 minus 95. That is 147. So we are going to plot R. Proton number is 95. Then neutron number is 147. So this is the point where we shall have R. Then nucleus R decays by emitting a beta minus particle to form nucleus X. So R 242.95 is emitting nucleus S with a beta particle, beta minus. So this is beta minus 0, -1. So proton number increases by 1, so this will be 96. Nucleon number does not change, 242. So the question wants us to draw a cross to represent nucleus S. So remember the graph is neutron number, not nucleon number. So the neutron number here will now be 242 minus 96, which is 146. So it means S is going to be 146 and 96. So 96 and 146, that is S. Okay, so that is the simple question. State the name of the other lepton in addition to the beta minus that is emitted during decay of nucleus R. Beta minus is accompanied by the neutrino. So we normally call it electron neutrino or simply neutrino. Electron neutrino or neutrino. A nucleus, sodium 2211, decays by emitting beta plus. A different nucleus is formed by the decay. State the name of other lepton that is produced by the decay. So it is beta plus. Beta plus is accompanied by an ant. Sorry. Beta minus is an electron. Sorry, this is electron antineutrino. Beta minus, that is neutrino. And then beta plus, that is the neutrino. Or sometimes you just write electron neutrino or electron antineutrino. Beta minus, antineutrino, beta plus, a neutrino. Determine the nucleon number and proton number of the nucleus that is formed by the decay. So we have sodium 2211 is decaying by emitting, let's say, nucleus X plus beta plus. Beta plus is 0, 1. Here nucleon number remains 22, proton number becomes 12. So we want the nucleon number. The nucleus decays by emitting beta positive. A different nucleus is formed. No, this is not, this is 10 actually. To balance, 10 plus 1 is 11, so it should be 10. Determine the nucleon number and proton number of the nucleus that is formed. So on the left, we have nucleon number is 22. On the right, it should also be 22. Proton number is, on the left, it is 11. This side should be 10 plus 1. So this is going to be 10 for X. A baryon consists of quarks that are the same flavor type. The charge of the baryon is -2e. They are the same flavor type, they have the same charge. So they are, because they are identical. Where is the elementary charge? Calculate in terms of E the charge of each quark. So 3, it consists of quarks that are the same flavor type. The charge of the baryon is 3e. I mean is -2e. We know that a baryon is a hadron which has 3 quarks. So a baryon has 3 quarks. So 3 quarks should give us -2e. So that means the charge of 1 quark is -2e over 3. Note that a baryon equals 3 quarks. It's a particle which has 3 quarks. That is a baryon. If they are the same type, then they have the same charge. So the charge of each quark is -2 over 3e. or the E is already there, -2/3. State a possible flavor type of the quark. So this is going to be, because the charge is negative, so this is going to be anti-up, anti-up, or it can be anti-charm, or it can be anti-top. Any of those, but commonly it is anti-up because we normally don't talk about anti-charm and anti-top in our everyday spoken physics language. An unstable nucleus. An unstable nucleus XAZ decays by emitting beta minus. Determine quantitatively the changes, if any, in A and Z. Determine the changes, if any, in A and Z. When X decays. So let's try to decay X here. So X is decaying. Nucleon number is A, proton number is Z. It is giving us beta minus, which is 0, -1, to give us a new nucleus Y. Nucleon number does not change, so the change here is going to be 0. Proton number here must be Z plus 1, so that Z plus 1 plus -1 takes us back to Z. So change in Z is going to be +1. Z increases by 1. In addition to the beta minus particle, another lepton is emitted during the decay. Whenever it is beta minus, the other lepton is electron and neutrino. A particle P is composed of an up quark and a down quark. Calculate the charge Q of particle P in terms of E, where E is the elementary charge. So an up quark, what is the charge of an up quark? So the up charge, we know that the charge of an up quark is +2/3e, and down is +1/3e. We saw these charges. So total charge, because they want the charge, so total charge is going to be +2/3e plus 1/3e, which is going to be 3e/3, and the charge is going to be +1e. So this is equal to +1e. So it is +1 because the e is already given. Particles P belong to two classes or groups of particles. State the names of these two classes. They say the particle P composed of an up quark and a down quark, and a down antiquark. So we have a quark and an antiquark, that is a meson. Those are mesons. But any particle which is made up of quarks is called a hadron. So these are hadrons. Particle P belongs to two classes or groups of particles. State the names of these two classes. It is a meson because it has a quark and an antiquark. It is a hadron because it is made up of quarks. I said the hadrons are of two types: the baryons, which have 3 quarks, and the mesons, which are made up of a quark and an antiquark. So those are the two classes. A nucleus of cesium decays by emitting beta minus particle to produce a nucleus of an element X and an antineutrino. The decay is represented by that. So P, this is a beta minus, so P is going to be 0, and R is going to be -1. Now we can balance the equation. A proton number We have 55 on the left should be equal to S plus R is -1 plus 0. So S is going to be 55 plus 1, which is 56. So S is 56. We can check a Q. On the left, we have 137 nucleon number. On the right, we have Q plus P was 0 plus 0. So Q is 137. That one is done. Off to the last page. State the name of the class or group of particles that include beta minus particle and the antineutrino. These are automatically leptons. Those are leptons. A particle Y has a quark composition down, down, down. That is a hadron. D represents a down quark. A particle Z has a quark composition anti-up, down. That is a meson. Show that the charges of particle Y and charge and Z are equal. Let's check. Charge of Y. The charge of Y is going to be down, down, down. So that is -1/3e plus -1/3e plus -1/3e. And this is going to be -1e. Then we can check charge of Z. Charge of Z equals to, it is anti-up and down. And anti-up, if up has a charge of positive 2/3e, that is for up, then anti-up is -2/3e. So this is going to be -2/3e plus a down quark has -1/3e. So this is LCM is going to be -3e/3, which is -1e. Hence, charge is the same. Hence, equal charges. State and explain which particle is a meson and which particle is a baryon. A meson, we have said it is made up of a quark and an antiquark. So Z is a meson. Z is a meson because it has anti-up and down. So Z is a meson because it consists of a quark and an antiquark. A meson is a particle which consists of a quark and an antiquark. Then Y is a baryon. Y or down, down, down is a baryon because of 3 quarks. A baryon is a particle which is made up of 3 quarks. I think this is the last question in nuclear physics. Fluorine is an isotope that decays to an isotope of oxygen and emission of beta plus. Complete the nuclear equation for the decay, including all the particles involved. So it is giving us oxygen plus beta plus, which is beta positive 0, 1. Beta positive is accompanied by a neutrino or an electron neutrino. So we try to balance the equation. So this will be 8 and the nucleon number will be 18. So that equation is complete. Note that beta positive is 0, positive 1. A quark in the fluorine nucleus changes flavor during the decay. State this change of flavor. So we see that the proton number has reduced. In other words, a proton has changed into a neutron. The neutron number is the one which has increased. So since a proton has changed into neutron, so we can say that an up quark changes to a down quark. A hadron has a charge -2e, where E is the elementary charge. State and explain whether the hadron is a meson or a baryon. So we can check. Remember, baryon has 3 quarks. Yet a meson has a quark and an antiquark. If a baryon has 3 quarks, I don't see any combination where the total charge will be -3e if I have 3 quarks. Because no, it can't be a meson. It must be a baryon, because if we have 3 quarks, 3 quarks or 3 antiquarks, each having charge -2e over 3, when I multiply this by 3, that gives me -2e. Those are 3 antiquarks. If it is a meson, remember a meson must have a quark and an antiquark. The possible charges of a meson are actually 0 or positive or -1, because it has a quark and an antiquark always. So mesons can only mesons can only have a charge of 0 or positive or -1e. Those are the mesons, 0, positive or -1e. So the hadron is a baryon. The hadron is going to be a baryon because mesons you can always check their combinations. Because it is a quark and an antiquark, it is always either 0, positive or -1e. But for baryons, they can have charges as high as that. Or you would say it must be 3 antiquarks. Because the largest negative quark charge is as the largest negative quark charge is -2 over 3e. When I multiply it by 3, it gives me -2e. So it must be 3 antiquarks. State a possible quark composition for the hadron. State a possible quark composition for the hadron. I've said it must be 3 antiquarks. And we can now find, I have already said -2 over 3e is giving us times 3, it gives us -2e. So this could be 3 antiquarks, 3 anti-up quarks. That is, it could be anti-up, anti-up, anti-up. Or it could be anti-charm, or it could be anti-top. But most commonly, the anti-up quarks are more common. Okay, so I think that marks the end of particle physics. We should meet. I'll see you in dynamics. My next unit will be dynamics. I hope you have enjoyed this. Sorry for any mistakes. Just know that I am human and I'm bound to make mistakes. You can always raise a complaint. You can write a comment. You can email me. I can always try to clarify. See you in dynamics. I hope this has been useful. Thank you and bye bye.